Right, we're launching in 2024, and it'll be about a 6-year cruise. Right. So the flybys of Mars and Earth happen in 2025 and 2026, respectively, and then we arrive at Jupiter in late 2030. So we'll have some time to think a little bit, do a little more research, which is important because there's a lot more we need to understand in terms of fundamental data related to Europa. So then the actual, after arrival at Jupiter, there's about a 6-month period of getting into orbit for the main science flybys of Europa. So we'll begin our science operations in 2031.
Welcome. AstroTalk UK is a not-for-profit podcast on astronomy, science and spaceflight. Launched in 2008, it's produced by me, Gurbir Singh, a writer based in the UK. I produce this podcast for my own education, but frankly, it allows me to meet fascinating people doing interesting things. It's primarily for my own education, and I share it as a free educational resource. No ads, no subscriptions, and you don't need to log in. For more, see the About page on astrotalkuk.org. Episode 108, NASA's Europa-Clipper mission. The Europa-Clipper mission, due for launch in 2024, will arrive and orbit Jupiter in 2030. The third spacecraft to do so after Galileo in 1995 and Juno in 2016. The Pioneer and Voyager missions were flybys. The primary objective, as the mission name suggests, is the investigation of Jupiter's moon Europa. Called Europa-Clipper after the 19th century merchant ships that shuttled between ports at the high speed then available. Europa-Clipper will orbit Jupiter, not Europa. This is one of Jupiter's moons that shows strong evidence of a subsurface water ocean. During its 4-year mission lifetime, it will fly by Europa dozens of times, looking for conditions suitable for life. Dr. Steven Vance talks about the mission's goals and current state of readiness. This was recorded in Athens during Cospar 2022. Dr. Steven Vance, you're an astrobiologist and a geophysicist studying the mechanics of icy ocean worlds. I heard about the Europa-Clipper program a long time ago when it first came out. You were probably at high school at the time. It's been a long time in the making. What's the current state of play with the Europa-Clipper mission?
Yeah, I'm really excited that the Europa-Clipper mission is nearing completion of its spacecraft instruments. We have a tour designed to explore Europa, and we're excited to be launching in 2024.
Now, it's been a long time in the making. When was it first on the design?
Well, the concept, even with the name Europa-Clipper, I think can be found in writing in 1999. So as soon as Galileo returned strong evidence for an ocean in Europa, at that time people were already thinking about some kind of mission to return.
Right.
And people have talked about orbiting Europa and landing on Europa. And in fact, the main concept for exploring Europa that's discussed in the previous decadal survey, the study that NASA roughly follows in planning its spacecraft mission. So that decadal survey from 2013 discussed a Europa orbiter.
Right. So this is a mission to the Jupiter system and focusing on Europa, the main, one of the interesting moons, one of the many in the solar system. You mentioned Galileo, it's one of the earlier programs that went to Jupiter.
Yeah.
Which other spacecraft, earlier missions to Jupiter and currently JUICE, have informed the kind of questions that Europa will focus on addressing?
Well, so Galileo's the main one, but even before Galileo, the two Voyager spacecraft that NASA sent to explore the entire outer solar system on what was called the Grand Tour. Right, they flew through the Jupiter system, and it just happened that in 1979, people realized that there might be a strong tidal interaction between the moons.
Right.
So prior to the launch, there are press graphics suggesting that Europa might be the least interesting of the 4 Galilean satellites.
Right.
And only just before the arrival at Jupiter was it determined that Io might be volcanic, and thus Europa might as well. And so it's exciting that Voyager confirmed Io's volcanism,
Right.
and revealed Europa to have an interesting geological surface.
So when you say volcanism, this is an icy moon. It's not like volcanoes on Earth. So what's the sort of activity? What's the structure of the current understanding of Europa that makes it interesting to go there for this quite interesting mission?
Yeah, well, so it might be volcanism like on Earth. On Earth, a lot of the volcanism that happens is under the ocean, in the seafloor.
Right.
And that kind of volcanism creates seamounts. It creates the Hawaiian Islands, for example. And it creates vigorous hydrothermal systems where life can exist independent from photosynthetic life on Earth's surface. So that's all very intriguing, given that Io is volcanically active. Perhaps Europa also has volcanoes. But you also make a good point that what we see of Europa's surface is all ice. And our best picture of Europa is a geologically active ice shell, itself of an intrinsic interest, globally fractured, ostensibly continuously fracturing, and so we hope that we might see active geology when we get there. And the ice is only perhaps as thin as 3 kilometers, but it could be as thick as 50. And so in either of those scenarios, there's a good chance that Europa-Clipper's radar can see through the ice and determine how thick the ice is, to see the boundary between the ice and the ocean.
Now, one of the interesting observations from Voyager was Io. That really was a volcanic eruption that was the first ever detected beyond Earth. So the two worlds, Io and Europa, are quite different.
That's right. And it's worth emphasizing that Io is more volcanically active than Earth. So it's the most volcanically active body in the solar system. Something like 2 watts per meter squared of heat coming out of the surface. So it's estimated it's about a factor of 10 as much heat at Io as at Europa. But the details really need to be determined. So they are very different worlds, but they probably formed together at the time that Jupiter formed. And Io, Europa, and Ganymede, at least, are involved in this intricate dance where they have harmonized orbits. So for every 1 orbit of Europa, Io orbits twice. And this isn't by chance. They've exchanged angular momentum. They've been tugging on each other, and so they shepherd each other in their orbits. And what this means is that their eccentricities may have changed through time, and they might exchange eccentricity. So sometimes Europa might be more tidally dissipated than it is currently, or less. And similarly, Io may go through periods of more intense and less intense activity.
So chemically, Europa is perhaps the attraction it has, and why NASA is going there with the Europa-Clipper program, is that there's water. Now, how much water is there? Where is it? And a bit like Enceladus, are there any plumes that you observed so far?
Plumes from Io?
From Europa.
Sorry. So there is tentative evidence of plumes from Europa. In fact, there was pretty compelling evidence returned from some Hubble observations in 2012, around 2012 and 2013. Those have not been repeated, and so it seems that if there are plumes, they are not happening all the time. So if there are plumes, then obviously there's some sort of a break in the crust to allow this water, and that would be interesting. Well, have any breaks in the ice crust been detected so far? Well, okay, so even without plumes, it's notable that the linear features crisscrossing the entirety of Europa's surface, many of them have this double-ridged aspect, which might be explained by periodic opening and closing of fractures on the surface. And so those fractures might reveal warm ice from below. And so one vision for that is that the warm ice is extruded a little bit with each opening. And then when the closure happens, that warm ice is pushed up and builds a little bit of the ridge. And so over thousands of cycles, you can build up a ridge that's hundreds of meters high and kilometers across. So none of that attests to direct communication of the ocean with the surface. But similarly, plumes that were observed by Hubble, and it might have been happening at the time that Galileo was there, there's some evidence for that, they wouldn't be directly communicating with the ocean. Instead, the ice probably churns about either through double diffusive, or sorry, through convection in the ice, or through other geological processes in the ice. You might end up moving materials from the ocean toward the surface. Yep.
So there's going to be quite a few instruments on board Europa.
Yep.
Can you just run us through the complete payload set and then focus on some of the more interesting, from an astrobiologist point of view, payloads that you
Sure. So I like the way you framed that. I'm happy to highlight the instruments. I want to emphasize they all work together.
Right.
And so the overall goal to understand Europa's habitability is only met through the combination of the instruments.
Yep.
But the way we describe it is, there's a remote sensing suite of instruments. So multiple cameras from the ultraviolet out to the radio. So we have an ultraviolet instrument, 2 visible cameras, a near-infrared camera, which is important for mapping absorption features for organics, important for life if we're looking for biosignatures. A thermal instrument that will allow us in the mid-infrared to be able to look at the heat signatures, even including from plumes, but also from other kinds of activity. And then again, the radar instrument that can peer through the ice. So along with those instruments, there's an in situ suite. And so the in situ suite of instruments consists of 2 mass spectrometers, a gas mass spectrometer called mass specs, that will be able to take gases from the atmosphere of Europa and from plumes and detect in detail their composition. For example, the presence of methane and oxygen, ratios of CO2 to oxygen, things that were really important for figuring out the pH of the ocean of Enceladus. Similar investigations might be undertaken at Europa. And so the other mass spectrometer is a dust detector. And so you can imagine dust particles, tiny microscopic dust particles, nanograins, being ejected from Europa's surface, either by radiation or meteorite impacts or by plumes. And so the dust analyzer can sample those and similarly can look for salts and organic materials that are on the surface. And by mapping the distribution of those features, can correlate those with geological features on the surface. So if we can identify a geological feature as being relatively recent, and perhaps even find a thermal signature of that activity, and look at its organic content, then we have strong evidence for material from the ocean and possibly material that provides hints of even life. So we can constrain possible metabolism and possibly presence of materials indicative of life. But I can finish the instrumentation just real quick. I don't want to underemphasize the other 3 remote sensing instruments, which are the magnetometer and the plasma instrument. Those work together to characterize the magnetic field around Europa. And it's the magnetic field that can tell us where the ocean is, how electrically conductive it is, and thus what the salinity is. And then the gravity and radio science instrument, which is basically an experiment looking at the Doppler shift of radio waves, can tell us the interior structure and the density structure. And that's how we figure out if Europa has a metallic core, and possibly if Europa's interior is volcanically active.
It's a fascinating collection of instruments, and as you say, it's the combination of the data that will give you the most powerful understanding of the structure and chemical constituents. One of the things you said there was in situ measurements, and in situ measurements to me is one of the most fascinating developments in recent technology, because now you can actually go there and taste and smell what's in the atmosphere or from the plumes of Europa. in order to do that, we're going to have to get pretty close to Enceladus. In
to Europe, yeah. It'd be nice to get close to Enceladus as well, but not for this mission.
Right.
Yeah, certainly. And so, it's worth emphasizing that the Europa-Clipper mission is not an orbiter, and so we won't always be close to the surface.
Right.
However, by having multiple flybys, the mission can be constructed in a way that we fly as close as 25 kilometers to the surface, possibly even closer.
Wow.
So you couldn't do that if Europa had an atmosphere, because the atmosphere would slow down the spacecraft. So we're going to get really, really, really close to the surface. Yeah.
And this is the one of the incredible things about doing this kind of investigation for the first time. You don't really know how close you can get to the surface of Europa, what plumes there might be, and if you are getting very close, there will be potential risk to the spacecraft if there are particles which are...
Yeah, so the Cassini investigation of Enceladus was also careful in its investigation of the plumes, and only late in the mission did they fly directly through the plumes at a really low altitude. But they determined that it was safe to do so, and the suite of instruments and the spacecraft are designed to tolerate those conditions. A plume sounds like a really dangerous environment, like walking through a waterfall, but really it's a diffuse spray. It's like more like walking through an aerosol cloud from hairspray, say. So not that much of a problem. There's another danger aspect in terms of getting that close to the surface. The propulsion engineers work very hard to design the trajectory based on assumptions of Europa's gravitational field, and so they have to make small corrections in the trajectory during the course of the trajectory, including accounting for revisions of Europa's shape. So as we use the radio science suite to get Europa's gravity data, and as we map the surface with our cameras, those engineers will be able to refine the trajectory, which will allow us to more safely get close to the surface. So it's a really complicated, intensive bit of work. And
that's another incredible, in my eyes, capability that not only, especially NASA, but other space agencies have developed in navigation, and it's so incredibly high precision and small tolerances that they can work to these days. So you highlighted that Europa is going to be, the mission Europa is going to be orbiting Saturn, not Europa itself.
Jupiter.
Thank you.
a lot of us have Saturn and Enceladus on the brain. I definitely relate.
And Titan as well.
And Titan.
So Europa-Clipper is going to be orbiting Jupiter, not the Moon itself, not Europa. So which other moons of Jupiter do you anticipate having close flybys off as well?
Yeah, so the science focuses on Europa, but as part of the trajectory, part of getting close to Europa, the mission will use flybys of Ganymede and Callisto. We want to stay away from Io because it's deep in the radiation environment of Jupiter, and so we will have fairly close flybys of Ganymede and Callisto, and currently there are calibration measurements planned, but those calibration measurements are very similar to the measurements we'll be making at Europa, and I'm very hopeful that we'll get some great science from those measurements.
Oh, it's going to be terrific science, and I'm sure images as well. So you've going to be going to tons of instruments, well, quite a few. Which one of those instruments, are you associated with any one in particular?
Well, I was working with the MassSpecs instrument for quite a while. My job currently is actually as co-lead for the Habitability Assessment Board. So this is a group that works to ensure that that all of the measurements are working together, and that the science team is on top of all the latest astrobiology research. So don't ask me to pick a favorite instrument.
and I think, just as you emphasized earlier, the end product is going to be a combination of the measurements and data that collectively all the instruments will pick up. There's quite a few instruments. What's going to be the size and mass of the spacecraft?
Yeah, so those are numbers I don't have right at the tip of my tongue.
Right.
I know the wingspan of the spacecraft is 30 meters.
30,
so it's
30.
Yeah, 30. So it's going to be quite impressive to look at.
Now, I'm guessing that's mainly the solar panels.
It is. It is mainly the solar panels, and it's something like 5 meters high. So it's a tall spacecraft as well.
Yeah.
So.
And with all the instrumentation on board, I seem to remember there's something like almost a third of a ton, about 300 kilograms. That's quite a heavy, big, meaty spacecraft. How are you going to launch it? Which launch vehicle are you going to use?
So so the launch vehicle, it'll be on a SpaceX.
Right. So a Falcon Heavy then,
Falcon
I guess.
Heavy, yes.
Right.
Yeah. Expendable. Yeah.
And it's so big, and even with that, it's not going to be a direct journey from the Earth to Jupiter.
That's right. So there will be 2 flybys, first of Mars and then of Earth. And so, yeah, it's intriguing to think of what kind of imagery we'll get of Mars and then of Earth on the way to Jupiter. Yeah.
And these flybys of Earth and Mars are for gravity assist.
Yeah.
But so you will be activating all of the instruments at Mars and maybe on the
No. So that's worth emphasizing. So. In fact, most of the instrument suite will remain dormant prior to arrival at Jupiter.
Right.
This is both a cost-saving measure and also a safety feature.
Safety for the instruments.
Yeah, we want to commission them only as we get close to Jupiter,
Right.
and that's all in work still. Yeah. Yeah, we'll see what happens with that.
What's the duration of the mission planned for Europa?
Yeah, so just right. So some of the timeline. Right, we're launching in 2024, and it'll be about a 6-year cruise. Right. So the flybys of Mars and Earth happen in 2025 and 2026, respectively, and then we arrive at Jupiter in late 2030. So we'll have some time to think a little bit, do a little more research, which is important because there's a lot more we need to understand in terms of fundamental data related to Europa. So then the actual, after arrival at Jupiter, there's about a 6-month period of getting into orbit for the main science flybys of Europa. So we'll begin our science operations in 2031, and those will continue. The first half of the mission will be, I think, 9 months, and then we take about a 9-month break. And reconfigure the orbit so that we can investigate the other side of Europa.
Right.
So for the first half of the mission, it's the side of Europa that faces away from Jupiter, because Europa is fixed in its orientation relative to Jupiter. And the second half of the mission, which will resume at the end of that 6 months, will be multiple flybys of the side of Europa that's facing Jupiter. You can imagine that's a little more risky. Yeah.
And as you were saying earlier, Jupiter is quite a strong, has a strong electromagnetic emissions. Yeah. Even when you're flying between Europa and Jupiter, I'm sure the engineers made sure it would be safe to do so.
Yeah, well, so I think some of the risk from the second half of the mission is more about being in eclipse, so not having a direct view to Earth for part of the flyby. Although I don't think that happens very, very frequently. But the main risks about being close to Europa are really just being in the most intense part of Jupiter's radiation environment. So the Juno spacecraft currently currently orbiting Jupiter has a similar problem. It has a highly elliptical orbit, and so it works very hard to stay out of the radiation environment close to Jupiter. But even with those precautions, you incur some radiation dose, and so it's expected that as the spacecraft ages over those few years of the investigation, the optics, for example, will degrade. Glasses tend to cloud up under radiation, that sort of thing.
So it's interesting you mentioned the large size of the solar arrays because it's so far away from the sun, and the eclipse, which might potentially prevent sunlight from getting to the solar arrays. One of the options that NASA has used in other space missions, deeper solar system space missions, is a radioisotope thermal generator for power supply. Why was it that an RTG option was not selected for Europa?
Yeah, I definitely was around for those discussions. I don't know if I want to go into it a whole lot, but as you mentioned, RTGs would have made the spacecraft a lot smaller, lighter, easier to maneuver because the solar panels are a big lever arm, right? It's like having your arms out while spinning around. So we're less nimble, but we're also in some sense a green spacecraft. We don't have to worry about our own radiation. We don't have to worry about environmental concerns upon launch. And as you might imagine, those environmental concerns incur a cost. And so a lot of the reluctance to use RTGs was about trying to keep the mission cost low.
That's fascinating. I remember the debate again. I think it was when Cassini was launched. There was a lot of people from the environmental movement complaining about that, and it's nice to see that NASA and other space agencies are considering that option at least. And
yeah, to the extent that we can, it's great to use solar power. I do want to emphasize that RTGs and in general nuclear power, I think would be really exciting for use in space, and in some sense, it's one of the safest applications. And there's a bit of a communication issue, I think, around the safety of the nuclear fuel. As I understand it, the fuel pellets themselves are pretty robust.
And interestingly, Apollo 13, when it came back, the service module ended up in the Pacific Ocean, which had one of these RTGs in there, and it was didn't cause any damage or concerns. But as soon as you say radioisotopes or nuclear source of energy, people do tend to draw their own conclusion very quickly first, and then think about what it actually means. So good to see that that's taking place in NASA in their considerations, as well as the pollution from the propellants in rocket fuel, which is fascinating.
Well, if I can make a plug for a book related to Europa-Clipper, so David W. Brown is an author, a science writer. He has a really compelling story in a book called The Mission. It really chronicles a lot of the people who were involved in the getting Europa-Clipper going. It includes a discussion about the choice of nuclear versus solar, including some of the politics around Cassini and a sort of notorious 60 Minutes interview that changed a lot of public perception about nuclear.
Okay, so we've got a couple of years to wait before launch, then a couple of flybys of Earth and Mars, and then about 2030 it arrives. It's going to be very exciting during the mission, but just in closing, what's the plan for end of life? Cassini had a very spectacular downfall. What's in the plans for Europa?
So that hasn't been fully determined yet. It would be exciting to crash into Ganymede if we're able to do that. I'll emphasize that we're very careful to avoid crashing into Europa. It's an abundance of caution. Planetary protection requirements might allow us to do that, but we couldn't necessarily guarantee that we wouldn't get material into Europa's ocean on a timescale of about 10,000 years. So it's safest to instead crash somewhere else.
It must be. I mean, I'm sure with all spacecraft, all space agencies take the utmost care in terms of decontamination prior to launch, but nevertheless, there's that small possibility, and that's why you make sure that it doesn't crash on.
And I mentioned earlier the care that the propulsion engineers, the trajectory design engineers take in allowing us to get close to the surface, and some of that is just to make sure that with every small maneuver, adjustment of the trajectory, we have minimal risk of hitting Europa. And so understanding the gravity environment will be very important.
So it's about 8 years before it arrives in Jupiter. I'm assuming you'll still be associated with the program?
I plan to be, yes.
Well, we'll check in with you again then, hopefully.
Well, that sounds nice,
And Dr. Steven Vance, thank you very much indeed. Appreciate it.
Thank you as well.